It's noon now, so I can say good afternoon. So I invite Francois Tilmani to just chair this session. There are 3 short presentations. One of them, the second one is by Zoom. Francois.
So welcome back for the last series of talk. It's my pleasure to introduce Sumit Mishra, who will tell us about local global principles for norms and multinorms over semi-local fields.
Thank you. So I would like to thank all the organizers, so, Professor Prasad, Professor Rapinchuk, Professor Sury, and Professor Tralle for organizing this great conference, and also for giving me this opportunity to speak here. I'm going to talk about local global principle for norms and multinorms. So I'll start with our number fields. So our number fields, we have a celebrated result of Hasse, 1931, which states that the local global principle holds for norms, our number fields, for finite cyclic extensions. And for quadratic extensions, it was proved by Hilbert in 1897. So what is this local global principle? So for example, let's just take the field of rational numbers. So then this states that if we have a L over Q, a finite cyclic extension, which means we have a finite Galois extension with Galois group cyclic, then if we pick a non-zero element in Q, then it is a norm globally, which means lambda is in the image of the norm map from L star to Q star, if and only if it is a norm locally everywhere, which means lambda is a norm in the image of norm maps when we base change to these fields, the field of real numbers and the field of periodic numbers QP. So these are precisely the fields you get when you take the completion over Q, you take all the absolute values and take the completions. So that's how these fields arise. And these fields are examples of local fields, and Q is a global field. We call it local global principle. And so of course here one would ask whether this holds for finite Galois extensions in general. And the answer is no. So actually it even fails for Galois extensions with the Galois group Z mod 2 cross Z mod 2, which is like the smallest non-cyclic example you can think of. So it fails badly. So, this result can be stated in terms of algebraic groups as follows. So we can say that the local global principle holds for norm and tori associated to finite cyclic extensions over number fields. So, and in general, we can consider local global principle for a norm and tori and more general algebraic groups over number fields and also over more general fields. So today I will be focusing on a special class of fields called semi-global fields and study local global principle for norms over there. So what is a semi-global field? So let us start with a field K, which is a complete discretely valued field with residue field kappa. For example, we can take Lorentz series over field of complex numbers. The residue field is just the field of complex numbers. And let F be the function field of a curve over K. So for example, if you take a rational function field, we get this field. So such fields are called semi-global fields. So to repeat, semi-global fields are function fields of curves over complete discretely valued fields. Okay. So this there are some more examples. So this example we already saw. We can take any complete discretely valued field. So for example, we can take QP and take rational function field, or we can take Lorentz series over FP and take rational function field. And in these all, I am taking rational function field, but we can take some more, more general curves, so we can get fields like this. So these are some examples. So these fields. So let me spend a little time over geometry of these fields. So let R be a complete DVR, and with residue field kappa. And let K be the field of fractions of R. So as a running example, we'll just take this. So we take power series over complex numbers, and kappa is just complex numbers, and we have this Lorentz series over complex numbers. Now let C be a curve over K. So for example, we can take P1, and then finally we have we take function field of the curve over K. So we get a field F. So hence F is a semi-global field. So important non-trivial fact here is that we can choose a regular proper model of F such that the reduced spatial fiber is a union of regular curves with normal crossings. And for this example, it's quite easy. You can just take the model to be P1. So yeah. So now we can look at the dual graph. So what I'm going to say is we can associate a graph to this kind of field, semi-global fields. So if we have X, the reduced spatial fiber, which is a union of regular curves with normal crossings, where I is varying over a finite set. So what we do is we consider a graph whose vertices I corresponds to these CIs, and there is an edge between I and J, if and only if there is a closed point lying on both CI and CJ. So this way we get a graph. And again, important fact here is that whether the dual graph described above is a tree or not, it does not depend on the model we choose. So of course, there is a lot of choices for the models, but whatever choice we take, whether the graph is a tree or not, whether it has loops or not, it does not depend on the choice. So in case the dual graph for some regular proper model, and hence all regular proper models is a tree, that is, it has no loops, then we say that the graph associated to F is a tree. So this all was to say that for semi-global fields, we can associate a graph, and we can, this statement is well defined that the graph associated to F is a tree, because it does not depend on the model we choose, right? So and this will come up in the statements later. And for this special, this example, so since this was just rational function field, so the dual graph will be just a point. So of course, it's a tree. Okay, now in this setting, I want to define, first of all, what do I mean by local global principle? So let F be a semi-global field. Let omega sub F be the set of all discrete valuations on F. Then for any discrete valuation nu, we denote by F nu the completion of F with respect to nu. Now I guess we know how can I can mimic as we had in the case of number fields and define what is a local global principle. So now let L over F be a finite separable field extension. No. Any. Also, yeah. Thank you. So we say that the local global principle holds for norm on torus or norms associated to this extension L over F. If for any non-zero element in F, lambda is in the image of norm map from L star to F star. That is, lambda is a norm globally if and only if lambda is a norm locally everywhere, which means lambda is in the image of norm maps when we base change to all these completions. Okay, so in case of number fields, we were taking completions with respect to all the absolute values, so Archimedean as well as non-Archimedean. So here we are taking all discrete valuations and similarly defining local global principle. Okay, so now let me say a few known results about local global principle for norms over semi-global fields. So this is a result of Kolyothelin, Parimala, and Sury, which says that the local global principle for norm on Tori holds for finite cyclic extensions over semi-global fields. So it was the same result was true over number fields. It is true here as well. And however, the local global principle for norm on Tori does not hold in general for finite Galois extensions, which was again the case for over number fields, but we'll say there is a lot of difference. So for another, for counter example, let us assume that kappa is algebraically closed field and of characteristic 0. So just think of field of complex numbers. Let F be the function field of a curve over Lorentz series over kappa. So F is our semi-global field. So then Kolyothelin, Parimala, and Sury, they gave an example of failure of the local global principle for norm on torus, where the extension was Galois with Galois group Z mod 2 plus Z mod 2. And the graph associated to F is not a tree. So I have defined a graph, the notion of graph. So in this example, they were getting, the graph was not a tree. And actually, this is very important example. So because this was the first example of failure of local global principle for connected linear algebraic groups over semi-global fields. In the same paper, they also proved this following positive result. So in the same settings, if we have L over F Galois extension with Galois group Z mod 2 cross Z mod 2, and once they assume the graph associated to F is a tree, then they could prove that the local global principle holds. Yes. Yeah. It's a Farovich group. Yeah. So now, so of course we can ask here, like this is a very particular case because the extensions are Galois with Galois group Z mod 2 cross Z mod 2, and there are some restrictions on kappa also. So we can ask, can we, the same question for like what happens if kappa is more general and this Galois extension is more general Galois extension, what happens? So now I can mention our results. So let kappa be a field, let F be the function field of our Lorentz series over kappa. So this is, F is going to be semi-global field. Let L over F be a Galois extension of degree n. Then a corollary of the general result we proved states the following. So I'll also mention the general result, but let me first give a corollary. So assume that kappa is algebraically closed, but now I'm not asking it to have characteristic 0. So it can be of any characteristic, and the field, the extension L over F can be any Galois extension as long as characteristic of kappa does not divide the degree. This is kind of a not so unnatural condition. Once you have this, then if the graph associated to F is a tree, then the local global principle holds for this field extension. So this is clearly a generalization of the result of polyethylene, Parimala, and Suresh, because they were assuming characteristic 0, and this Galois extension was just Galois extension with Galois group Z mod 2 cross Z mod 2. Here I am allowing any finite Galois extension as long as characteristic does not divide this degree. Okay. For example, this if you take the characteristic 0 case, then any finite Galois extension, as I mentioned that if you take rational function field, then this precondition is satisfied. Hence, for this particular field, if you take any finite Galois extension, we have the local global principle. Okay, so the slogan here is tree implies local global principle, which is not like, in this setting it's true. Okay, so in order to state the general result, I will need to recall the notion of R equivalence. So let G be a linear algebraic group. For a field extension L of F, let GL be the set of L points of X. Then we define R equivalence as follows. We say that 2 points x0 and x1 are R equivalent. We denote it by x0 tilde x1. If there is a rational map from P1L to GL, so that at 0 it is x0 and at 1 it goes to x1. So this gives a equivalence relation, and which we called R. Yeah, P1 over L. Yeah. Thank you. Now here we have some special elements which we call R trivial elements. So let E be the identity element here. Then we just collect all elements which are R equivalent to E. We call it RGL, and these elements are called R trivial elements. Okay. So now I can state the general result. So let K be a complete discretely valued field with residue field kappa, and F is the function field of a curve over K. So F is our semi-global field. Now, and let L over F be a Galois extension of degree n. So now we need to have some assumptions. So assume that characteristic of kappa does not divide n. Assume that K contains a primitive nth root of unity, let's say rho. Now we have this slightly technical condition. For all finite extensions, kappa prime over kappa, and for all finite Galois extensions, L over kappa prime of degree d dividing n, we have this condition. So this is just the norm 1 points. Norm 1 points when you look at the extension L over kappa prime. So things, elements of L which have norm 1 when you send it using the norm map to kappa prime. And this is the R trivial elements I said. So it says that if you look at norm 1 elements here, then up to R trivial, up to R equivalence, they are generated by roots of unity. Okay, so this is what it means. And finally, we have this important condition that the graph associated to F is at tree. So then we have the local global principle for norms associated to this extension L over F. So, so let me just say, so if kappa is algebraically closed, then the second bullet point and third bullet point as trivial, like trivially satisfied. So hence we are back to that corollary which I said. So now let me say something about multinorms. So multinorms is, so we have talked about local global principle for norms. So what we can have instead is we can have finitely many extensions. And then instead of local global principle for norms, we can ask local global principle for products of norms. So that we call multinorms. So our number fields, this has been studied quite extensively by, for example, by Erlemann, Kolyothelin, Sansok, Platonov, Rapinchuk, Prasad Rapinchuk, Polio Rapinchuk, the Marche, Polio, Eva Bayer, Lee, and Parimala, and others. So I'll just go over the results we have for multinorm case, semi-global fields. So again, we have this notation, let K be a complete discretely valued field. The residue field is kappa. And let F be the function field of a curve over K. So F is our semi-global field. So then we have this result. So if L1 and L2 are two abelian extensions of the field F, each of degree n, both are degree n abelian extensions, and assume that kappa has cohomological dimension less than or equal to 1. For example, just think algebraically closed or a finite field. Then assume that n is square free and the characteristic kappa does not divide n. Then the local global principle holds for multinorm torus, or like multinorm torus is just like non-torus, you have more than one extension. So you take Wheel restriction of GM for all this, take the product, and then this goes to GM and take the kernel. Yes, yeah. Okay, so we have this. So here the important case is when this n is a prime. So both are degree p cyclic extensions. So once you prove the result for that, then it follows for this. Okay, and so we can also consider in the case of quadratic extensions, which we have more. So if we have finitely many quadratic extensions and assume that the residue field kappa is algebraically closed and the characteristic is not equal to 2. So this will this usually comes up. Characteristic should not divide the degree. And if the graph associated to F is a tree, then the local global principle holds for associated multinorm torus. So for this, we prove for any number of quadratic extensions. Okay, let me now say that our number fields, I have not mentioned the result, but our number fields, what we have is, if you take quadratic extensions, then if you take 3 quadratic extensions, that it may fail. But if you take 2 or like more than 4, then it always holds. So, but here we are proving that if you assume this condition, then it's holding for 3 also. I mean, of course, it's holding for any finite number of quadratic extensions. And here you notice that here there is no tree condition. This is a strong result because we don't need any condition, any tree condition. And actually, it's we have to use this result to prove this. And when we apply this here, then we need that tree condition. And yeah, so these are the references. So the results are in these 2 papers, and the results of Kolyothelin, Parimala, and Sury are in these 2 papers. So Thank you.
Thank you. Do we have any questions for Sumit? Yes.
Perfect? No?
The residue field should be perfect? No?
No.
Really?
So in certain results, we need it to be algebraically closed actually, but,
Yeah,
but in general, like the first result I said,
oh.
whatever conditions were there, it
Like to get the special fiber of the regular model to be, you know, this kind of normal crossing stuff that doesn't require perfect residue field.
no, it is actually work by Lippmann, and there's a paper
Yeah.
of Lippmann.
Yeah,
Using that, we can get it for in our setting. This one.
right, but
This one.
the
Yeah.
normal crossings. Okay, I'll ask you separate. What's your definition of normal crossings if the residue field is not perfect?
Okay, we'll discuss.
Yeah, yeah.
Thanks. Any other questions? If not, let's thank the speaker again.